Traditionally, thermodynamics has been defined as a study of energy and its transformations. Okay, so you could see that from the name. Okay, so thermo relating to energy and dynamics relating to transformations. In the bigger picture of thermodynamics, however, we can also define it as the study of restrictions on the possible properties of matter or on permissible physical processes. Okay, so thermodynamics, it pretty much tries to establish relationships between the different properties of matter and the way that these properties can be changed after undergoing processes. So recall in our discussion of equations of state, we wanted to establish relationships between pressure, volume, temperature, and number of moles of a system. So we're pretty much describing the properties of matter in a particular state, right? So in the larger picture of thermodynamics, however, we want to relate all the parameters of the system, including its internal energy, entropy, as well as its other properties that we just mentioned. Okay, so why do we want to do this? We want to do this so that we could describe and make predictions about the behavior of a system in terms of its energy as well. So we could start looking not only at the properties of matter, but also the processes that matter undergoes. Okay, so we're going to be looking at changes in the state of matter before and after a process. Okay, so while the study of thermodynamics can get a little bit abstract, in these abstractions of these concepts, we find that we could apply them in many cases. Okay, that is, we have universality. So it pretty much applies to all systems. So the laws that govern how machines and engines run, for example, are the same that governs the reactions that fuel stars, and even the laws that govern biochemistry and biology. Okay, so the laws that govern life, right? Okay, so thermodynamics is a very universal field of study. All right, so before we start, let's proceed with some definitions. In studying thermodynamics, we want to divide the universe into two parts, okay, namely the system and the surroundings. Okay, so the system, this is just part of the universe under study. Okay, so the rest of the universe that's not in the system is just called the surroundings. Okay, so we can divide our system from the surroundings using a wall. Okay, so the wall is pretty much a barrier, and the type of wall that we use defines the system's so-called boundary conditions. Okay, so let's look at different types of systems that we can have, right? So if we have a wall that is both permeable and diathermal, we will have an open system. Okay, so an open system is characterized by a free exchange of matter and energy. Okay, so living organisms, they are open systems. Okay, so we breathe out and breathe in air, for example, and could easily exchange heat with our surroundings. Okay, other types of systems include a closed system. Okay, so if our wall now becomes impermeable, okay, so we no longer have an exchange of matter with our surroundings, but we could still exchange energy. Okay, so most of the simple systems that we'll be talking about in our thermodynamics discussions will be closed systems. Okay, so we won't be seeing any change of the amount of matter in our systems for a closed system. Right, so another type of system is an isolated system. Okay, so now our wall is going to be impermeable and adiabatic. Okay, so there's no exchange of both matter and energy. All right, okay, so let's now look at different types of properties of a system. Okay, so overall a property, this is just a macroscopic observable that defines the state of the system. Okay, so we have two major types of these properties. Okay, so we have extensive and intensive properties. Okay, so extensive properties, they're just going to be dependent on the amount of matter present. Okay, so for illustrative purposes, let's have this system that is divided into four parts. So overall, if a property is extensive, if we take the property of part 1, part 2, part 3, and part 4, and we sum them all together, okay, the sum of that is going to be the property of the entire system. Okay, so mathematically we could express this as the following. Okay, so property X is an extensive property, so that means the sum of the property of part 1, part 2, part 3, and part 4 is equal to the whole. Okay, so examples of extensive properties include volume, internal energy, enthalpy, entropy, and number of moles. Okay, so we could easily see this with volume. Okay, so if we take the volume of 1, 2, 3, and 4 and we sum them all together, okay, that would give us the total volume of the system. All right, so we also have another type of property, which is the intensive properties. So intensive properties are going to be independent of the amount of matter present. Okay, so again, for illustrative purposes, let's take this system that's divided into 4 parts. Okay, so if we have an intensive property, okay, so if we measure the intensive property of part 1, 2, 3, and 4, okay, they're going to be the same as the property of the whole. So this is going to be in contrast to extensive properties that are additive. So to express this mathematically, okay, so the intensive property of the total system is going to be equal to the intensive property of part 1, part 2, part 3, and part 4. Okay, so that means you could just measure the intensive property of one part of the system and you pretty much get the intensive property of the whole system. Okay, examples of intensive properties include temperature, pressure, density, and molar quantities such as molar volume, molar enthalpy. Okay, so we could use temperature as an example. Okay, so in this particular system, okay, if we measure the temperature in part 1, 2, 3, and 4, the total temperature of the system is not going to be the sum of the individual temperatures that we just measured. Okay, so actually the temperature should be the same in all of these parts of our system, and the temperature of the entire system should also be the same as those taken from the parts. All right, so that is an intensive property. All right, so those are just some terms that we wanted to define before we proceed with our more formal discussion of thermodynamics. Okay, so of course, when we start talking about thermodynamics, there's also another thing that we need to define before we go into anything else. That is, what is energy? We use the term energy a lot in everyday life, but of course, what is it exactly? Okay, so a lot of textbooks define energy as the ability to do work. Okay, so of course, when you analyze this definition, you start to wonder, okay, what does it mean to do work? Okay, so when we look at the definition of work, however, work is also defined as a method of energy transfer. Okay, so this definition is kind of circular because if we look at this, we're pretty much defining energy as the ability to transfer energy. Okay, so not very informative. Okay, so another definition that we could use is this one by Dave Watson. Okay, so Dave Watson defined energy as a property or characteristic of matter that makes things happen, or in the case of stored or potential energy, has the potential to make things happen. Okay, so by making things happen, we are causing changes. Okay, so changes in properties of our system, like changing the temperature, changing the pressure, changing the volume. Okay, so this is due to energy. Okay, so this is what we're interested in thermodynamics after all. Okay, so we're interested in analyzing changes in the properties of our system after undergoing processes. Okay, so all of these changes are driven by energy. All right, so let's look at this a little bit more closely in terms of our system and our surroundings. Okay, so our system is going to have its internal energy. Okay, so internal energy is symbolized by a capital U. Okay, so internal energy is just the total energy that's in the system. Okay, so changes can happen if we have a transfer of this energy to our surroundings or to other systems. Okay, so we could transfer energy by work for one, or we could also transfer energy by heat. Okay, so let's just do an additional clarification on heat. Okay, so heat is also defined as a method of energy transfer. Okay, so we'll talk about these different ways of energy transfer a little bit more closely later on, but I just want to clarify that heat is not something that a system inherently has. Okay, so heat is commonly used in everyday language as something that an object has. Okay, so for example, when an object is hot, sometimes we say that, oh, it has a lot of heat. Okay, so but keep in mind that it doesn't really make sense in the thermodynamic definition of heat because heat is a process. Okay, it's a method of transferring energy. Okay, it's similar to work. Okay, so we never really say that an object has a lot of work. Okay, what we usually mean by that, however, is that an object has an ability to do work. Okay, similar to what we probably mean by when we say an object has a lot of heat. Okay, we mean that an object has the ability to transfer heat. Okay, so just to clarify the meaning of heat. Okay, So overall, these are two methods to transfer energy, okay? So when we're transferring this energy, then we're going to be changing the internal energy of this system, okay? So the change in this internal energy can also be associated with a change in other properties of this system. Okay, so of course, if we're transferring this energy, so it has to go somewhere, we're putting it into the surroundings, right? So the surroundings also has its own internal energy, U, okay? So since it also has this internal energy, the process could also go in the reverse way, okay? So that means that the surroundings could also transfer energy as work or heat into the system. Okay, so let's look more closely at this internal energy. What is it exactly? Okay, so we said it was the total energy of the system. Okay, so how do we look at what that is exactly? Okay, so we could divide the internal energy into two major parts. Okay, so we could define internal energy as the total sum of kinetic energy and the total sum of potential energy. Okay, so we talked about kinetic energy before. So kinetic energy is the energy of motion. Okay, so in physics we also have a mathematical description of kinetic energy. Okay, so kinetic energy, this is defined as 1/2 times the mass times velocity squared. Okay, so using this definition, we could also derive units for energy. Okay, so this is 1/2 mass. SI unit of mass is kilograms. SI unit of velocity is meters per second, so this is squared. Okay, so if we divide this into two parts, then so we have 1/2, okay, kilograms. Okay, so let's split off one of the meters over here, meters per second squared times meters. This over here, kilograms meters per second squared, this is your Newton, and you have your meter. Okay, so your Newton meter, this is equivalent to your joules. Okay, so your joule is your energy unit. Okay, so another energy unit that is commonly encountered is your calorie. Okay, so 1 calorie is equivalent to 4.184 joules. Okay, so the calorie, it's actually related to the properties of water. Okay, so it's still used a lot. So you might need to use this unit conversion in some of our calculations. Okay, so keep in mind that the calorie, this is a little bit different from the calorie that we see in our food labels. Okay, so the stuff that we see in our food labels is usually capital C, calorie. Okay, so capital C calorie, this is just equivalent to 1 kilocalorie. Alright, so just for clarification on this. Okay, so some labels also use the joule, the kilojoule, as a unit of energy. Alright? Okay, so let's also look at this part over here, our potential energy. Okay, so our potential energy, so there's lots of different types of potential energy. Okay, so our potential energy is just our stored energy. So we could have chemical potential energy, electrical potential energy, nuclear, gravitational, lots of different types of potential energy. Okay, so this is the part that probably makes things a little bit more complicated in determining internal energy of a system. Okay, so there's lots of different types of potential energy, and all these things are very, very hard to measure. Okay, so ultimately, if it's really hard to measure potential energy, it's also very hard to measure our internal energy. Okay, so it's never really possible to get an absolute value of the total internal energy of our system. Okay, but luckily we're not really interested in determining the exact internal energy of our system. Okay, what we're usually interested in, after all, are changes, right? Okay, so we're interested in how our internal energy changes after it undergoes a process. Okay, namely if it undergoes a transfer of this energy as work or heat. Okay, so we're interested in the change in internal energy. Okay, so delta U, which is equal to the internal energy of the final state minus the internal energy of the initial state. Okay, so again, we're not really interested in absolute values of internal energy, but rather changes. Okay, so just to look at this graphically, if we have U initial as our initial state of the system, okay, and it undergoes a process, okay, so say that our final state is down over here. Okay, we're just interested in this change over here, okay, the delta U, okay? So if delta U is negative, we have a decrease in our internal energy. And if delta U is positive, we have an increase in our internal energy. Okay, so note that U final is in a higher internal energy state. All right. Okay, so same thing goes for surroundings actually. Okay, so we could also have a change in internal energy in our surroundings after this process over here. Okay, so we also have a corresponding delta U for our surroundings. Okay, so if we have our system and it transfers some of its internal energy towards the surroundings, there has to be a relationship between the way that delta U of our system changes and delta U of our surroundings changes. Okay, so intuitively we know that we're transferring some of this energy, right? So it has to go somewhere. So if ever we're decreasing the internal energy of our system, okay, this has to lead to a corresponding increase in the internal energy of our surroundings. Okay, so the change in internal energy of our system is going to be in equal magnitude but opposite sign to that of our surroundings. Okay, so this principle is overall just the first law of thermodynamics. Okay, so the first law of thermodynamics tells us that energy cannot be created nor destroyed. Okay, so it only could be transformed or transferred. So when we're saying transform, that means our energy could take different types of forms. Okay, so it could be in terms of kinetic energy, or it could be in terms of potential energy. Okay, so transferred, okay, meaning that if we have a certain amount of energy being transferred from one system to another, okay, so all of that energy has to be accounted for. Okay, so none of that energy is going to magically disappear. Okay, so this energy transfer could occur through many other ways. It could occur through heat, or it could occur through work. All right. Okay, so let's look at different ways in which we could measure changes in internal energy while keeping in mind the first law of thermodynamics. Okay, so keep in mind again that there's two major ways in which we could change our internal energy of our system. Okay, so that is through a transfer of energy via work or via heat. Okay, so when we're going to be considering changes in energy, let's consider infinitesimally small changes. Okay, so we could represent infinitesimally small changes by differentials. Okay, so let's look at the differential of internal energy, du. Okay, so if we're looking at infinitely small changes in internal energy, okay, so this is going to be the sum in the amount of small work that is being done, as well as the infinitely small heat that is being transferred. Okay, so note that I wrote the differentials of internal energy and for work and for heat in different ways. Okay, so we just need to clarify the difference between these types of differentials. Okay, so for internal energy, okay, so this type of differential, this is called an exact differential. All right, and the differentials for work and for heat, okay, so in thermodynamics we call these inexact differentials. Okay, so we can see the significance of these differences when we start to integrate these differentials. Okay, so when we're integrating, we're going to be integrating from the initial to the final state in order to get the overall change during a process. Okay, so let's try to integrate both these sides. Okay, so we're going to start from the initial. Okay, so that's going to be u initial and then u final. Okay, so in the case when we're trying to integrate inexact differentials, however, okay, so we can't exactly define our initial and our final states. Okay, so ultimately what's going to happen here is that we could get an expression when integrating exact differentials. So this will be u final minus u initial, okay? But for work and for heat, which are inexact differentials, okay, so these are going to be path dependent, okay? So it's going to depend how you're going to be integrating these differentials. So we just write this out as the total work and the total heat during the process, okay? So this over here, we could express this as delta U is equal to W plus Q. Okay, so the change in internal energy is just equal to the work that was done as well as the heat that was transferred. Okay, so why do we have to make this differentiation between exact differentials and inexact differentials? Okay, so this has something to do with state functions. Okay, so We can express differentials as exact differentials if we're dealing with so-called state functions. Okay, so state functions are usually expressed as capital letters. Okay, so this means that they are path independent. Okay, so meaning that if we're evaluating on a differential, it only depends on the final and the initial states. So for non-state functions, okay, like heat and for work, these are path dependent. Their quantities are going to depend on the path that was taken in order to get from the initial state to the final state. Okay, so an analogy for this situation over here is when you're climbing a mountain. Okay, so the state function in this case is just the difference in heights. Okay, so you started from this low altitude and then you went to a higher altitude. Okay, so state functions just care about the final and the initial states. Okay, non-state functions, however, they are going to depend on the way that it took you to get to the initial to the final state. Okay, so here's one path. Okay, so this is going to be a different value compared to the longer path that you took for B. Okay, if you went around the mountain rather than going straight up. Okay, so overall the value of Q, it's going to depend on the path that it took for W, and W is going to depend on Q. Okay, so that's why we call them inexact differentials, because we can't exactly get their values without knowing the other quantity. Okay, so to get a more concrete energy-related example, okay, we could use the example of discharging a battery. Okay, so let's assume that these two batteries, they have the same amount of internal energy. Okay, so assume that they're fully charged at first. Okay, so there's two different ways in which you could discharge the battery. Okay, so in one method, okay, so you could just connect it to some copper coil and then you're going to waste all the energy as heat. Okay, so if you connect these two terminals, okay, so all of the energy contained in the battery is just going to be dissipated as heat. Okay, so you're able to reach the initial to the final state just by releasing heat. So the amount of heat, however, that you're going to transfer is going to depend on the amount of work. So in this particular case, there's no work. Okay, so you're able to say that all of the heat is just equal to delta U. Okay, so another way of using up the battery is through useful work. Okay, so you can connect it to an electric fan. Okay, so the electric fan is going to do mechanical work. Okay, however, keep in mind that sometimes your electric fan can also heat up a bit, so some of the energy is going to be lost as heat. So overall, there are two ways in which you used up the energy of the battery. Okay, so you dissipated some of that energy as heat, and you also used some of that energy to do work. Okay, so two different pathways. Okay, so again, the amount of work that you would do over here is going to depend on the amount of heat that you would release. Okay, so again, knowing the amount of work would depend on the amount of heat that you would have done. Okay, so again, these are your non-state functions. Okay, so for the most part, however, work and heat are the only non-state functions that we'll be looking at. Okay, so most of the other parameters that we'll be investigating in our discussions are going to be state functions. All right, so let's look at work and heat a little bit more closely. Okay, so we'll look at different ways in which you could calculate the work done by a system as well as the heat involved in the process. Okay. All right, so let's first look at work. Okay, so from your physics, recall that work is defined as when we apply a force and we cause displacement. Okay, so let's look at infinitely small work being done. Okay, so we have our inexact differential of W. So this is going to be equal to a force applied, okay, and the corresponding infinitely small displacement dx that was done. Okay, so overall we could use this picture over here. Keep in mind that whenever we're doing work, we need to have a displacement. Okay, so a typical physics example is if you're pushing against the wall. Okay, so you're exerting a force against the wall, but since there's no displacement, regardless of all the effort that you're doing in pushing the wall, there's no work because, again, there's no displacement that occurred. Okay. However, if your wall is able to move around a bit, okay, so all that effort of pushing that wall actually led to a displacement, so that means you actually were able to do some work. Okay, so overall, displacement is necessary for work to occur. Okay, so for the most part, the type of work that we'll be investigating will be pressure volume work. Okay, so in our initial treatments of very simple systems where we will be looking at the expansion and contraction of a gas against an external pressure, okay? So let's look at this process a little bit more closely. We'll use an example system over here, our ideal gas. Okay, so let's first look at expansion, okay? So keep in mind that all these principles I'll be discussing for expansion will also apply for contraction. But overall, let's look at this gas system over here inside a container with a movable frictionless piston. Okay, so our initial state is that we have volume 1 at a pressure 1 of the gas at constant temperature, okay? So the gas is also exposed to this external pressure over here. Okay, so this is the initial state. So keep in mind that the gas is also going to be exerting a force on the sides of the container. Okay, so it's also going to be pushing up against this piston here, right? Okay, so there's also an external pressure pushing down, but the gas is pushing up in the opposite direction. Okay, so if we're interested in looking at an expansion process, okay, so there has to be condition as to the values of the external pressure and the pressure of the gas, okay? So if our gas is going to expand, this means that the pressure exerted by the gas, the upward force, has to be greater than the downward force of the external pressure, okay? So overall, we mean that in order to have an expansion process, P1 has to be greater than P external, okay? So if that's the case, we have a net force going upwards that's able to push this piston upwards and increase the volume of the gas. Therefore, we have an expansion process, okay? So overall, we see this displacement over here, okay? So what can we say now about the final pressure of the gas compared to the constant external pressure over here, okay? So keep in mind that the gas is going to expand only up until a certain point, okay? So it's going to expand up until the point where it reaches mechanical equilibrium, okay? So mechanical equilibrium meaning that the upward force exerted by the gas is just balanced out by the force exerted by the external pressure over here. Okay, so the implications of this is that P2 is now equal to the external pressure. Okay, so keep this in mind. Okay, so always whenever we're doing expansion or contraction, okay, the final pressure of your gas always has to be equal to the external pressure. Okay, so this is the condition for mechanical equilibrium. Okay, so the forces being exerted are now equal, and there's therefore going to be no net movement of this piston. All right. Okay, so let's also investigate how we could evaluate work, okay, in this particular case. All right. Okay, so what is work again? So we defined work as dW is equal to force times displacement. Okay, so let's figure out what this force is exactly. Okay, so keep in mind that we're dealing with pressures, right? So how do we define pressure again? So pressure is defined as a force exerted over an area. Okay, so let's also look at what dx is. Okay, so in this particular case, the displacement is this particular distance over here. Okay, we were able to displace this piston by this distance here. Okay, so let's get an expression for force. Okay, so force, this is going to be equal to PA. Okay, so we could replace PA with one of the pressures over here. Okay, so what's going to be constant in this particular case is the external pressure. Okay, so since we're always interested in looking at the process with respect to the gas, okay, the external pressure is going to be equal to negative P external, okay? So our force overall is negative P external times the area. Okay, so what is the area exactly? We're talking about the area of the piston over here. Okay, so let's bring these two things together. So dW, this is going to be equal to negative P external times your area times your dx, your displacement. Okay, so note that if we multiply an area by a displacement, so this is a height, right? This is ultimately going to be a volume. Okay, so we could write the work as negative P external times dV. Okay, the change in volume of the gas. All right, so this is overall our expression. Okay, so let's look at this a little bit more closely as well. So again, our expression was dW is equal to negative P external dV. Okay, So let's look at the significance of this negative sign over here, okay? So if we're doing an expansion process, okay, so again, in our expansion process, okay, the initial pressure, so P1, this was greater than the external pressure, right? So it's your gas that is actually pushing against this piston. Okay, so it's your gas that's doing the work, okay? So expansion process, this means that your gas is doing work on the surroundings, okay? So that means that the energy to do work is coming from the internal energy, right? Okay, so let's also look at dV. For an expansion, okay, dV is equal to V final minus V initial, right? Okay, so that means that V final is larger, so that means dV, this is going to be a positive value, okay? So if dV is positive, okay, so that means during an expansion process, that means that our work, this is going to be negative, okay? So this is our notation for work, right? So if our system is doing work, that means the work is going to be negative, okay? So why does this make sense again, okay? So recall again our expression for internal energy. So du is equal to dw plus dq, okay? So if our gas is doing work, okay, this is going to be negative, okay? So doing work decreases the internal energy of the system, okay? So that makes sense, right? Because where does the energy come from to do work? Okay, it's going to be coming from our internal energy, okay? So it makes sense that the internal energy of the system is going to decrease if the gas is doing work, all right? Okay, so keep in mind that this is the notation that we're going to use, okay, in our discussion for thermodynamics, okay? So some references might use the opposite notation, okay? So there tends to be a different notation for physics and chemistry, but just keep in mind our particular notation, okay? So if the gas is doing work, okay, the sign for work is going to be negative, all right? Okay, so let's get a graphical interpretation for this process, okay? So in our example, we're treating the system as being under a constant temperature. Okay, so we're changing the pressure and the volume of our system, right? Okay, so we have an ideal gas, so that means the gas follows Boyle's law. Okay, so Boyle's law tells us the relationship between pressure and volume at constant temperature. So here we have a Boyle's law PV isotherm, all right? So let's check out what's happening over here. Okay, so let's draw out what volume 1 might be. Okay, so here's volume 1. Okay, so the corresponding pressure in the initial state, okay, so let's figure out what that is. Let's draw up a line here. So this is going to be the corresponding pressure at volume 1, okay, and at the constant temperature here, all right? Okay, so in order for an expansion to occur, right, so we said that P1 has to be greater than the external pressure, okay? So let's just set some arbitrary external pressure, okay? So P1 has to be greater than external pressure, so that means the external pressure has to be lower. So let's say that's over here, all right? Okay, so if we're trying to figure out then what the final state is going to be, okay, so we said that the final state is going to be defined by mechanical equilibrium. So that means that the external pressure is going to be equal to the final pressure, P2, okay? So overall, we could figure out what the final state is. This over here, this is going to be pressure 2, okay? So pressure 2, this is going to be defined by a certain volume, volume 2, okay? So this is our expansion process, okay? So let's look again what we said about work, right? dW is equal to negative P external dV, right? Okay, so if we integrate this, okay, with respect to the initial and final states, our work is going to be equal to, so P external is constant, right? So we could take this out of the integral sign. So this is going to be negative P external delta V, okay? So let's look at the graphical interpretation of this, okay? So P external, where's P external? This is right over here, okay? What's delta V? Delta V is right over here. Okay, so that means if we multiply P external by delta V, we get like this area, right? So this part over here is actually represented by the area under here. Okay, it's a rectangle, right? So this is the height, that is this part here, this is your P external, okay? And then your length is your delta V, okay? So there you have it. We could represent work just by looking at the graph of a pressure and volume curve, okay? So this part over here, this is your work, right? Okay, so let's look now at another process, okay? So we could also do the same treatment for a contraction process, okay? So again, we have our gas inside this container with a frictionless movable piston, and we have this, this constant external pressure being exerted, and of course our system is at, again, constant temperature, okay? So this is just an example. We could always change the conditions later on, okay? So overall, our initial state is V1, P1, right? So we want to have a contraction process, okay? So again, let's consider the pressure exerted by the gas, okay, versus the external pressure. Okay, so if we want this piston to be moving down in order to contract the gas, that means that the force going downwards has to be greater than the force going upwards. Okay, so this implies that P external is greater than the initial pressure. Okay, so when we look at what's going to happen afterwards, okay, so we have a contraction process now since this force is greater. Okay, so ultimately it's going to be contracting only up until a certain point. Okay, so this means that P external is going to be equal to the final pressure of our system. All right, okay, so this is pretty much the same treatment again, okay, so regardless of whether it is an expansion or contraction process, okay, the final pressure of your gas has to be equal to the external pressure, okay, so this again, this is your mechanical equilibrium, okay. The same treatment can be applied, okay, so the displacement that occurs is over here, so we could also write down our work as force times displacement, and ultimately we still get the same expression, okay, so dW is going to be equal to negative P external dV, okay, so in this particular case, on the other hand, okay, so we're doing a contraction process, right, dV is going to be negative, we're decreasing the volume, right, okay, so overall the sign for work, okay, so negative times negative is going to be positive, okay, so keep in mind again that what's doing the work here? It's not exactly the gas, but rather it's the surroundings, okay? So ultimately in this case, okay, so let's just write this down again. So dW is equal to negative P external dV. So the change in volume is going to be negative, so our work is going to be positive. Since we're doing a contraction process, okay, so it's the surroundings that is doing the work, okay? So surroundings does work on the system, okay? So the positive sign here makes sense because the energy is being transferred from the surroundings to the system, okay? So that means that we expect that the internal energy of our system is going to increase, okay? So du again is equal to dw plus dq, okay? So in this case, if work is being done on the system, dw is positive, okay? So we expect that this work done on the system is going to cause an increase in our internal energy of our system, okay? So overall, again, we have an energy transfer from the surroundings towards the system. Therefore, the internal energy of our system is expected to increase. Okay, so we could also do the same graphical interpretation of this entire process, okay? So again, let's consider what our initial pressure is, okay? So let's treat our initial pressure as a little lower this time, okay? So let's say that it is over here, okay? So P1, okay? So we have a corresponding volume for that, okay? So our corresponding volume is V1, okay? So we said in order to have a contraction process, the external pressure has to be greater than the initial pressure. Okay, so let's say that the external pressure is right here. Okay, so we also said something about how the external pressure is going to be equal to the final pressure. Okay, so this is our final pressure here, P2. So this corresponds to the volume, the final volume, V2, okay? So we're going from V1 to V2, all right? So we also mentioned how work is equal to negative P external times delta V, right? Okay, So if we're getting a graphical interpretation this time for contraction work, okay, we're looking for a rectangle, right? Okay, so the height of the rectangle is going to be the external pressure, so this is the height, and then the width is going to be equal to the change in volume, delta V, okay? So that means in contrast to expansion work, this over here, this is going to be our contraction work, okay? So larger rectangle, okay? So look at this here. This is our work done during contraction, okay? So it's a lot of work to contract the gas, okay? Okay, so let's look at a little bit of a variation of the constant temperature, constant external pressure expansion process. Okay, so let's check out what happens if we do this in multiple steps. Okay, so say that we want to expand our gas from volume 1 to volume 3. Okay, so for our initial state, the initial pressure was over here, right? So this is P1. Okay, and then our external pressure is down here. So overall, the work that was done to expand the gas from volume 1 to volume 3 is this shaded rectangle over here. Okay, so this is the work. Okay, so what happens, however, if we do this in multiple steps? Okay, so let's try to do this in 2 steps instead of 1 step. Okay, so that means we're going to be introducing a different external pressure for the first step. Okay, so let's look at this first step over here. Okay, so instead of expanding it directly to volume 3, we're going to expand it first to a volume 2. Okay, so keep in mind that we still have the same initial pressure, right? Okay, so this external pressure is still lower than the initial pressure, but note that's a little higher compared to the one-step process. Okay, so it's a little closer to the initial pressure. But overall, our first step did this amount of work here. Okay, so we went from volume 1 to volume 2. Okay, so we could introduce a second step to go to the final volume. And there we have it. Okay, so overall we have one step here which did this amount of work. Okay, and then the next step is represented by this shaded rectangle here. Okay, so when we did it in 2 steps, note that the amount of work done by the gas increased, right? Okay, so for a 1-step process, the work is represented by this rectangle here, right? However, if we do it in a 2-step process, a little bit more work, right? So that additional work is represented by this additional shaded region, okay? So let's try to do this in 3 steps, okay? So when we do it in 3 steps, okay, so note that we have 3 external pressures. So note that this external pressure over here started to become closer to our initial pressure, but overall we did more work. Okay, so the gas did more work when it was expanding it in 3 steps. Okay, so 1, 2, 3. Okay, so also note that the area under the curve starts to get shaded more and more. Okay, so you're doing more work when you do it in multiple steps. Okay, so what happens if we keep doing this? Okay, so what happens if we start doing this an infinite number of steps? Okay, so if you do this an infinite number of steps, what do you expect to see under the curve over here? Okay, we expect that the entire region under the curve is going to be shaded, right? So if we do this in an infinite number of steps, okay, the amount of work that you would do would be equivalent to the area under the pressure volume curve. Okay, so what can we say about the external pressures for each of these infinite steps? Okay, so note again from our previous observations that if you increase the number of steps, the external pressure keeps approaching the initial pressure of the gas. Okay, so this is the pressure of the gas, right? Okay, so it comes closer and closer to this. Okay, so overall over here, what we could say here is that this is the initial pressure of the gas, right? Okay, so the initial external pressure was pretty much equivalent to the pressure of the gas. Okay, so we're doing that an infinite number of steps. So if you expand the gas a little bit, the pressure is going to decrease. So the external pressure is also going to adjust to the pressure of the gas in the infinite number of steps. Okay, so in each step of the way, you have mechanical equilibrium that was established. Okay, so the pressure of the gas is always going to be equal to the external pressure of the gas. Okay, so it's kind of weird, right? How when you're doing an expansion process, in each step of the way you had mechanical equilibrium. So mechanical equilibrium means that nothing's going to happen anymore, right? So that's why we call this reversible work. okay? So each step of the way is reversible, okay? So it's actually not very realistic to have this whole process happen, but it's a nice theoretical limit as to what could possibly happen when we're doing pressure volume expansion work, all right? So this over here, this represents our maximum work done by the gas during expansion, okay? So when we're trying to calculate reversible work, okay, it's no longer going to be a rectangle, right? So rather it's the entire area under this curve, right? Okay, so how do we evaluate this reversible work, okay? So what comes to mind when we're talking about areas under the curve, okay? What comes to mind are integrals, right? Okay, so keep in mind that our equation again for work, this is equal to dW is equal to negative P external times dV. Okay, so the tricky part about this now is that the external pressure is no longer constant for the entire process. Okay, recall again what we said earlier is that when we're doing reversible work, the external pressure constantly adjusts to the pressure of the gas. Okay, so each step of the way we have this condition here. The external pressure is equal to the pressure of the gas. Okay, so how do we express the pressure of the gas? Okay, so we're dealing with an ideal gas in this particular example. Okay, so we could use the ideal gas equation. PV is equal to nRT. Okay, so pressure of the gas, this is equal to nRT over volume. Okay, so we could write our expression for work as negative P gas dV, replace the expression for P gas with our ideal gas expression over here. So ultimately we have dW is equal to negative nRT over V times dV. All right. So if we're integrating this, okay, so we could integrate this from the initial to the final state, okay, so integrating our inexact differential will just give us the absolute value of our work done for the process, okay, and if we're integrating this, however, we're doing it from the initial volume to the final volume, okay, so note that number of moles is constant, okay, in this particular example, and our temperature is also constant, so we're dealing with an isothermal expansion or isothermal PV work, okay? So in this particular example, we have negative nRT outside of the integral sign, dV over V, okay? So VI, VF. Okay, so what's the integral of this? Okay, so recall again that this is going to be your ln. So we could evaluate work, okay? Let's write a little note over here. Work reversible as negative nRT ln VF over VI, okay? So this is our expression for reversible work for an ideal gas at constant temperature, okay? So note the conditions in which we can use this equation, guys, okay? So a lot of people get, just because they see an expression for work, that they use these equations for all cases, okay? But keep in mind that we derive this expression for an ideal gas and for isothermal conditions, reversible work. Okay. Okay. So what happens when we're doing the reverse, however? Okay. So we said how during expansion we had a maximum work. Okay. So what happens when we're doing the reverse? Okay. We're starting from this initial volume going to our final volume. So we're doing a contraction process instead, a compression process. Okay. So if we're doing reversible work, then it's not going to be the maximum work done by the gas, but rather if we're doing a compression, it's going to be the minimum work done on the gas. Okay, so recall again that if we do this in a one-step fashion, okay, so if we start from V1 over here and then we want to get to this final volume over here, okay, so this is our initial pressure, right, for a compression process, okay, and then our external pressure has to be equal to the final pressure, so this is our P external. Work is going to be equal to this large rectangle here, okay? So if we do this in multiple steps, however, okay, so another step, let's introduce this here. Okay, so we have this PV curve over here. Okay, so V1, let's say that this is the intermediate volume and this is the final volume. Okay, so again, our initial pressure is over here, P1, okay, and then our intermediate pressure, this is going to be our P external 1, so that means the work in the first step was this smaller rectangle over here, okay, However, it wants to get to the final volume, right? So that means the final volume corresponds to this second external pressure, okay? So the work for step 2 is going to be this larger rectangle here, right? So the drawing isn't perfect, but you could kind of see that we saved this amount of work done on the gas, right, when we did it in 2 steps. Okay, so if you do it an infinite number of steps, okay, so ultimately you'll shave off the rest of these parts that go beyond the curve, and we get this over here. Okay, so this again, this is the minimum work done on the gas during compression. Okay, so that is your reversible work. Okay, so reversible work, again, keep in mind that your external pressure is going to be equal to the pressure of the gas, okay? So if you imagine how that's happening, okay, so you have our piston here, right? Okay, so we have our pressure of the gas, external pressure, okay? So in each step of the way, according to reversible work, the pressure exerted by our external pressure, that by our surroundings, is going to be equal to the pressure exerted by the gas. So technically there's no net force, right? So it's kind of weird how somehow we're able to push this expansion while each step of the way we have mechanical equilibrium. Okay, so that means it's actually going to take an infinitely long time for this process to happen. So again, it's just a theoretical limit as to the possible work that could be done for pressure volume expansion or compression.